Alright, hello everyone. So in this video section, we're going to talk about viscous flow in pipes. In your textbook, we're covering chapter 8, 8.1 and 8.2. The learning objectives for these two sections are first to understand the characteristics of pipe flow. Right? So what are the characteristics for pipe flow, internal flow instead of external flow? Second, we need to understand the difference between laminar and turbulent. A third is to understand the difference between entrance region and the fully developed flow. We mentioned a little bit on this before, but we have to talk more about it. And the fourth one is to master the calculations in fully developed flow. Alright, so before we talk about the characteristics of pipe flow, we want to define something called internal flow and external flow. We say internal flow are flow fields which are bounded by boundary conditions, by plates, by pipe walls, and so on. External flows are something I refer to as flow over immersed bodies where the flow field is not bounded. If you look around the environment you are staying here, actually pipe flow is everywhere. For example, crude oil pipeline started from Alaska. It runs 800 miles, even more, taking crude oil, right? So it's all pipe flow. And you can think of something else, for example, pipes that carry blood throughout your body. That is pipe flow as well. And if you look around in your home or the dorm or in your classroom, we can see water pipes around you, right? So these are all pipe flows. So we studied this problem in previous chapters as well. For example, we studied pipe flow using differential analysis or dimensional analysis. These methods all can solve these problems with very severe assumptions. For example, differential analysis, we have to make sure the boundary conditions are simple enough, right? Then you can simplify your Navier-Stokes equation. And in control volume analysis, you make a bunch of assumptions such that you ignore viscous effect and so on. So in real world effects, in real world problem about pipe flows, we really don't want to ignore all these effects, for example, viscous effect. So we probably want to use a combination of experimental data with theoretical considerations and also dimensional analysis to provide us the more accurate results. So this is what we're gonna do in this chapter, which is to study the problem pipe flow in a condition which has much less assumptions in it. And here's the video. I'm gonna show you this video. In this video, you will see we inject a dye into this pipe flow, and you can see when we increase the flow rate, how well the characteristic of pipe flow change. All right, let's watch the video together. All right, you see at the beginning we have a very small flow rate, and you can see the flow has a very well-defined line as it flows, right? And then we start to increase the flow rate here. We start to increase the flow rate. All right, you see the dye start to be disturbed here and there, and here's vortices constructed. And you see all the molecules blurred into the molecules of the dye blurred into the flow around it much faster than at the beginning, right? And keep going, we increase the flow rate even larger and larger, and finally you see all the dyes just blur into the surrounding immediately, right? So you cannot define any line, you cannot define any line here. So here we showed you three different Reynolds number regions here actually. We haven't talked about it, but let's talk about Reynolds number and three different regions. Alright, from the video we just showed you, you have some intuition there, right? So when we increase the flow rate, you start from laminar flow, and then from a transition period you go to turbulent flow. So we all notice that when we increase the flow rate, flow start from laminar and turn into turbulent. But the flow rate itself, does it change the flow from laminar to turbulent? We say it doesn't. There's something else that involved as well, right? So something else, what are they? So there is a dimensionless parameter called Reynolds number that defines whether a flow field is laminar or turbulent. Reynolds number, by physical meaning, is a ratio of inertia forces over viscous forces. Alright? By definition, it is the density of the fluid times the velocity of the fluid times characteristic dimension over dynamic viscosity of the fluid. So here we talk about dimension here we're using here is characteristic dimension. What does that mean? So if I have a pipe flow, I might use diameter d instead of the length of the pipe. The characteristic dimension here is diameter. Alright? But if I have a plate, rectangular plate, I might use the length of the plate or height of the plate. So it is that characteristic dimension. You have to see what the situation is and to define what dimension you are using here. Alright, so here we're defining Reynolds number for pipe flow. We say that for pipe flows, Reynolds number for ranges for laminar flow, transition period, and turbulent flow are not precise numbers. We don't say, oh, this number is laminar flow or a certain number is turbulent flow. Instead, we give a range. And in engineering applications, we say the range is like this. When Reynolds number is smaller than 2100, we say this is laminar flow. And to be specific here, all the flow we're talking about are for pipe flow, right? So laminar pipe flow. And with Reynolds numbers higher than 4000, we say that is turbulent flow. Turbulent pipe flow, right? And in between these numbers, right? Reynolds number in between 2100 and 4000, this is transition. It is the transition between laminar and turbulent. Next, let's talk about entrance region and the fully developed flow. We say for any pipe flow, there's an entrance region, is where near the very beginning of your pipe, right? The flow has to enter this pipe. So let's take a look of this graph on your book. For example, we have this pipe flow coming out of a big tank. Alright, so at the beginning, at this region, we call it entrance region. Alright, so entrance region is defined by the boundary layers of this pipe flow meet with each other on the boundaries. Alright, so if you look at this flow, when it enters when the flow enters from a big tank into this pipe flow, it has viscous effect bounded by these flow pipes, right? Because of no slip condition, viscous effect, all the flow has to stick on the pipe, right? So there is a region on the pipe wall which is highly influenced by viscous effect, right? This region's highly influenced by viscous effect, and we call it boundary layers. And the inviscid core is this region here, which is not influenced by the boundary conditions or viscous effect. We call it inviscid core. So as the flow goes, the boundary layer actually change. If you see the boundary layer increase and increase and increase, and finally they meet with each other from the side, right? So this length from the beginning where the boundary layer starts to the time or the location where the boundary layer meet each other, we say this length is called entrance length. How do we calculate entrance length? We say entrance length for laminar flow and turbulent flow are different. You can think about why, right? Because the viscous effect, how important viscous effect is for that laminar flow and turbulent flow is different. So for laminar flow, we use this equation. LE, which is the entrance region length over the D, capital D, here means indicates the diameter of the pipe, equals to 0.06 times Reynolds number. All right, this is for laminar flow. And for turbulent flow, the equation is LE, which is entrance region length over capital D, equals to 4.4 times Reynolds number 216. Right? This is for turbulent flow. Then let's take a look at these two equations. Does they tell you something? For example, the first one, laminar flow. Alright, so laminar flow, entrance region length over the diameter equals 0.06 times Reynolds number. And we have mentioned that Reynolds number when it's laminar flow, pipe flow, and here we want to emphasize also we're talking about circular pipes. Alright, circular pipes. If your pipe has another shape, for example, rectangular pipe or other shapes, this laminar flow Reynolds number range will be different. Alright, so here specifically we're talking about circular pipes. When we have circular pipes, we have Reynolds number is about 2000. Alright, so if you look at this equation again, if I have 2000 plug in here, I have 1, 2, 3. Your entrance region length will be about some small number times your diameter, right? So when you have laminar flow, your entrance region will be comparatively a short region, right? But if you look at turbulent flow here, we have the equation LE over D equals to 4.4 times Reynolds number to 116, right? 16, which give you, let's take a look at this table. So we estimate for turbulent flow, entrance region length for turbulent flow at different Reynolds number from 4,000 up to 10 to the 7th. All right, so if I have typical, say, pipe flow application, my Reynolds number will fall in the range here. All right, fall in the range here. Then if I look at a highly turbulent flow, which is 10 to the 7th of Reynolds number, your LE over D will be equals to 90. What does that mean? That means your entrance length should be 90 times your diameter of the pipe, right? Which compared to laminar flow, in turbulent flow, your entrance region can be a comparatively larger number, which sometimes, if you are considering the beginning of the pipe, the entrance region of the pipe might not be ignored in your problem, depending on how long your pipe is. Usually your pipe is much longer than your entrance region length. And we say if this criteria is met, which means your pipe flow length is much longer than entrance region, we can simply say it is fully developed flow. which means you don't have to consider all the characteristics of the entrance lens. Next, fully developed flow. We say, let's bring up the book. We say, after the first entrance region, your flow is going to be very stable, fully developed flow. Alright, so fully developed flow is very stable, and when you, for example, sometimes there's little disturbances going on in your flow field. Alright, then your flow might go through a region called developing flow, and go back to fully developed flow again. Right, so this is what's gonna happen in fully developed flow usually. So in this chapter, please read carefully section 8.1. Section 8.2.1 to section 8.2.2, 8.2.4, and summarize the ready-to-use equations derived here. The methodology in fully developed flow, we already done this in using control volume analysis, differential analysis, and so on. So here it's just repeating all the examples we have done in class, and please go through them carefully yourself, understand the equation, understand the derivations, and summarize the ready-to-use equations. Alright, so we are going to talk about some examples using these ready-to-use equations in these examples in class. Alright, so this is it for this recording section, and make sure you read the book chapter 8, 8.1 and 8.2, specifically these sessions, alright, before you come to class, and I'll see you guys on Wednesday.